Now let us take a simple electrical problem. We saw it earlier also, but now we will try to model it using an effort mapping method. This is a simple resistance, inductance, capacitance RLC circuit in series with this power supply. Uh, One of the ways in which this system can be modeled is by indicating the potentials at these points. So because these potentials are efforts, so we take zero junctions, zero specifying the potential at the point A, this zero junction specifying potential at the point B, potential at the point C, potential at the point D. So all these four potentials have been modeled using these four zero junctions. Now, this source of effort, Vt, what it is doing is creating a difference of potentials between the points A and D. So you can see that this effort is equal to this effort minus this effort. So V is equal to VA minus VD. So that is done by placing a one junction here, which is an effort summing junction. Okay. Likewise, you also have between these points A and B, you have the potential at A, potential at B. What this R element does is it creates a difference of potentials between A and B. So you take the relative difference, you take the relative potential between A and B. So this effort is equal to this effort minus this effort. This one junction acts as an effort summing junction. Okay, so you can assign this R element here. Likewise, here you have the element I element connected here. Here you have the C element corresponding to this compliance connected here. So in this way, we find that we are able to completely model this simple system. You see, in our earlier model, we saw that it was connected like this. We could see that the bond graph appeared like this when we showed it earlier. But now in the effort mapping, we find that it looks like this. Now these two bond graphs are actually equivalent. How do we come to that conclusion? Let's have a look at that. So what you observe is that this zero junction here, it is redundant. This bond is connected to the zero junction and this bond is connected here. In fact, this zero junction is playing no role, it appears. So you can directly connect you can connect it with a bond directly like this. Okay, the power coming in is the same as that, there's power which goes out, and there's no other element connected here. So directly you can connect this bond here. In the same way, this zero junction also, it can be directly connected over here. So we could directly connect this like this. This also we can directly connect. Here also we can directly connect. And here also can directly connect. So you see that these zero junctions, they become redundant. Okay. So we can actually do away with these zero junctions and directly connect these bonds. Let us do that. So this is gone. Same way here also, this is gone. Here also, this is gone. Okay. Now, what do you observe next is that this one junction is the same. It's directly connected to this bond, directly connected here. Uh, so it's as good as this one junction can sit on this one junction itself. Okay. So all these one junctions can be merged into a single one junction. Okay. And that is what we have got here. We merge them all in the single one junction. And you can see now that the power that is coming in, okay, so this is indicating the potential of, there are two variables, effort and flow. So the effort here indicates the potential of this end with respect to this end. Okay, that's created by this source. So the voltage that is input is creating a difference of potentials, VA minus VD. Here you have this difference of potentials. It's a potential drop being caused by this R element. The potential drop is effort 4, which is given here, VA minus VB. It's the difference of these potentials. Likewise, here also, you have this effort 2, it is the potential of B with respect to C, and the potential, the effort here in this bond is actually potential of point C with respect to D. Uh, in fact, you can see that uh, if you write down all the variables of the efforts and the flows, you have all the variables of power indicated on the bond graph. You have, you can also start causaling this system. If you do the causal strokes on this system, you start with the sources. So this source of effort, so a stroke is placed here. All the other bonds, that doesn't help much because I think we can remove this. Let me just see if it can be done. Yeah. So we have removed all these causal strokes. Now let us do the causality for this. So we'll place the causal strokes one by one. So here we'll start with the source. We place a causal stroke here. Okay. So this is the end which receives the effort. So a causal stroke is placed. What about the other? What about the causality for the other bonds? So here you can see, if you take the C element, you put it in integral causality, it will have a stroke here. Okay. Next is this I element. If you place it in integral causality, the stroke will appear here. It's in integral causality. So the moment this I element brings in flow into this one junction, one bond is only allowed to bring in flow. So all the other bonds have to respect that. And so this R junction, this R element will take a causal stroke like this. So you see that flow has come into this one junction and it is accepted by all the other bonds. Only one bond is determining flow, and that is because it's a characteristic of the I element, this inductance, which will actually determine the flow, the current in this circuit. Okay, so it can take the difference of potentials. This I element will take the difference of potentials across it, but it will provide the current. It will determine the current uh, depending upon its characteristic. So the current is determined here. So this is about the causality for this system. We have seen all causality for this entire bond graph. Now we can see how many variables are there. We have uh, one C element, one I element. This C element is contributing its state Q1, which is actually the charge associated with this capacitor. So it is actually a generalized displacement associated with this capacitor. It's generalized, it's a charge, electrical charge. Here you have the generalized variable associated with this I element is its momentum. So in this case, it's the electrical momentum. It's the flux linkage associated with this winding, with the inductance element. So we represent it as lambda. So P2 is equal to lambda. This is actually the variable associated with this I element. What actually happens is this difference of effort which has been created across the I element, that is actually integrated by the I element. It determines the flux linkage or the electrical momentum, and it produces an output which is a current, which is a function of that momentum. So this is a straightforward relationship. It will decide what should be the flow in this circuit. Once this flow is determined, all the other bonds accept the same flow. So the current is the same in all these bonds. You can see here now that this C element is providing to this one junction an effort, and that effort is given by its characteristic, the characteristic of the capacitance. So this potential difference, which is determined by this C element here, is potential of C with respect to T. It is the potential across the ends of this C element. And that is because it's a linear element, it's Q upon C, Q1 upon C. Q is the charge and C is the capacitance associated with it. So we know that this constant 1 upon C, it represents, you can say, the electrical stiffness. C represents just the charge, okay, which is a generalized displacement, which is actually not a generalized displacement, but it's just this. It's just the capacitance associated with this charge. Okay, Q1 is the generalized displacement associated with this capacitance. So here we also have this R element. What this R element does, it has been provided with current, and it results in a potential drop across its end depending upon its characteristic. And assuming it to be a linear R element, we can say that R into I is the potential drop across it. So the effort, that is the voltage drop across this R element, is just R into I. Okay. So you can see here that the voltage that comes in is V. The power that comes in is V into I. The power that goes into this R element, which is lost forever, it's because this is a dissipative element. You can't recover this power. That is given by this E4 into F4. E4 is actually R into I multiplied by I. So you have Ri square. And you can see that it is a permanent loss. Ri square is always getting lost from here. This power is always getting lost from here, from this bond. Over here you have effort 2 into flow, effort 2 into flow 2, which is the same effort 2 into the current. That results in the change of electrical momentum and in the generation of a current, in the determination of a current through this I element. Here, for this C element, it takes the current integrates it, determines the charge, and produces a potential difference across it, which is a function of that charge. Okay, since it's a linear capacitance, it just um, produces a potential difference which is directly proportional to the charge Q1. So this is how you can model this simple electrical circuit.